Okay, hi, good evening, everyone. I hope we all had a very nice day. So today it's been a while at Machine Learning Lagos, and that's because we have just currently finished the recruiting of new team members, and we are starting with new people. So, welcome once again, and yeah, our regular technical sessions. So, as usual, the ground rules, please be respectful during the calls or during the sessions. Keep your mic muted unless you are the one speaking or you are asking a question. Engage, ask questions in the chat, speak once at a time, or you use the raise hand function before you speak so that we can, be orderly. Then keep the discussion on just the topic and the agenda so we don't go out of boundaries, then avoid spamming. Feel free to ask questions, and lastly, have fun session. So, yeah, as usual, welcome, then the session, then the Q&A, then any announcements and wrap up. So today we'll be looking at statistical approach to linear machine learning models, and it will be taken by Narcissus Sampson. So, I don't know. The bio was not collected from you. So, but what's on the slide is very simple. So we have that Sampson is a machine learning engineer and is a community member. I don't know why this is community. A community member of Machine Learning Lagos. So, over to you, Samson, for your session.
All right, everyone. Good evening. Okay, I hope everyone is seeing the screen. Hello.
Yeah, I can.
All right. So we'll be talking about the statistical approach to linear machine learning models. Um, Based on my experience, I love moving with a roadmap. So having this topic, the first question I would like to ask is I'm not asking you guys out though. So the first question I asked myself was why this topic? Why am I picking this topic? So the reason for this topic is because most ML engineers their their models fail because they ignore statistical assumptions. So this topic is being very volatile. It's being very crucial, yeah, for a statistical or ML engineer. So from there, we move on to the next reason why I'm choosing this topic, which is because interpretable is better and much more powerful than just predictive. Every ML engineer can predict, yes, but how do you interpret? How do you feed the data into the prediction itself? Which model are you trying to like work on? How is the data fit for the model you're trying to work on? So the third one is yes, we can all build a model, but not all models that we can build make sense. Some people can build a model that work, but it doesn't make sense. Some can build a model that makes sense, but it doesn't work. So having the basic knowledge of statistics into ML is a very crucial aspect of machine learning. So we go into that aspect today. So from this now, linear regression, why I mentioned the statistical approach to linear model is because linear models are more interpretable, like unlike the deep learning aspect of the black box because they are more complicated. That's why I call them the black box. They are very much complicated compared to the linear regression, which is more visible and easily understandable. So from there, we move on to what we'll be learning today. So we'll start from the intuition behind the linear models. We explain how the linear models work because it is very common for ML engineers to just like use models. Normally, you understand that yes, you're trying to predict a value, then you just input your data into it, then you predict a value. You don't know how the data is being how the data is working inside the model. You don't know the procedures, you don't know the assumptions needed by the model for the data to work accurately. That's why you see some people usually fight with predicting, trying to like improve the accuracy of their model. This isn't because the model is bad, but because they are nullifying the assumptions of the model. So just like a student writing an examination, yeah. So everybody have same question paper, right? But at the end of the examination, some question paper will be having higher mark compared to others. This is because the way a student's structure is writing, like is answering to the questions asked by the lecturer or the professor, is different from the way the second student is being addressed, is addressing his own answers. So this difference also matters. The way you address your data, the way you like follow the question promptly, they might just ask you to like answer 2 out of 4. But because you don't read the instruction, you don't read the assumptions of the question paper, you just answer it. That alone is giving you like some left behind marks. So that's just like some intuition. Like we need to know how these models work. What are their expectations? What are their assumptions? So from there, we'll move on to the next thing that we'll be talking about today, the assumptions that make them work. Some models don't need much assumption, just few assumption. But as an ML engineer, we are like, we are curious. Our model have to work. We need to like make the R score to be very, very, like 0.9, 0.8. But how is it? How are you sure that even that accuracy you're having is not being from overfitting? Maybe you've break some assumptions. You don't know. You're just like, this accuracy is just what I want. I want it to be around 0.8, 0.9. Then some people are killing their time on hypertuning, just trying to like maximize the efficiency of the model. So that's part of what we'll be talking about. Then how to check those assumptions. Yes, we mentioned those assumptions. How do we check those assumptions? How do we verify that certain data sets are following a assumption for a model? Sorry. So how do we check if the data sets are following the assumption we want to fit into the model? So those are what we'll be talking about today. Then when to trust the prediction. Yeah, you might have a very nice model that's giving you a very nice accuracy. You can be having 0.9 accuracy, like trying to predict is working well on the test sets, but how do you know? How do you trust the prediction that the model is giving to you? Also talk about that. And lastly, we move into the real world example with analysis because I believe in practical. So we can just work out some examples at the end of the lecture. So that's what we'll be learning today. Then we move on to explaining what linear model is. What is linear model? What is a linear model? Yeah, everybody have been hearing linear model, linear model. So what is linear model itself? Linear model is one of the simplest, most fundamental model. Like I said earlier, the black box and the linear model, yeah, exactly, and the regression models. Regression models are very flexible. They are easy to like understand, easy to interpret, but the easier they are to interpret, some people usually make it complex to themselves because they don't understand their assumption. So from there now, we have to like understand the fundamental models in statistics because linear models, they are fundamental models in statistics and machine learning. They are used to describe the relationship between a dependent variable of one or more independent variable. Yeah, we try to check the relationship between a dependent variable and an independent variable, where the independent variable might be either one or two or more. So that's a linear model. So from there, we move into the general equation of a linear model. So what is the general equation of a linear model? Basically, what I'll be talking about is if we are to like handle the linear models in ML, there are a lot of them. But for this lecture, I'll just be talking on the simple linear regression model. But in general, you can just follow up. So from this now, this is the formula for the linear regression, not even linear regression model, yeah, but it's for the linear model generally. So the beta knots, this y equals to beta naught plus beta 1 x1 plus beta 2 x2. Nobody likes formula, yeah. So we won't be going much into the calculation. But what I'm just trying to talk about is that we need to understand how this model works. What are their expectations? What are they assuming? So from this equation now, we'll just check out what they mean, what's like, what are they referring to, and yes. So the components, the y here is the target variable, that's the dependent variable, as we said earlier, that linear models measures the relationship between the dependent variable. This y here is the dependence variable, which is the output we'll be expecting from our model. Then the beta naught is the intercept. Sorry. Beta naught is the intercept, while the beta 1, beta 2 to beta p, they are the coefficients, or we call them the slope. Yeah, I'm using a statistical term here. Sorry. So for the x1, the x2, the xp, those are the input variable. Just like trying to predict the effect, like the sale of ice cream in a sunny day. You know, there are various factors that can influence it. You know, in a sunny day, you can say, okay, because the higher the sun, there will be a higher rate of ice cream sold. Yeah. So that's a dependence variable. That this rate of selling ice cream, which is y, is depending on the amount of sun, like the quantity of sun in that season. So for a rain, like for the rainy season, there will be less amount of sale of ice cream. That's just basic explanation. We won't be going into the calculation. So let's just move on to the next part. Next part, which is what are the statistical assumptions of these linear models? Yes, we mentioned the linear models to be this. Y equals to beta naught plus beta 1x plus beta 2x to blah, 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 blah. What are their assumptions? What do they expect? So we'll move on. So the first thing they expect is linearity. You check, is there a linear relationship between the independent variable, as I mentioned earlier, the sun, and the dependent variable, the sale of ice cream? Is there a linear relationship between them? Can we say after collecting your data sets, just check randomly, is it that higher rate of sunlight is giving a higher rate of sale of ice cream? You know, that's just to check, but we'll still be looking at how to check for these assumptions also, but this is just fundamental of it. So next one is, after checking for the linearity, are the dependent variable and the independent variable, are they linear? Are they having a linear relationship? So that's the first assumption of the linear model. If you should ignore this assumption, then your model is already failing. So next one is independence. The error are independent of each other. Or what this is trying to like tell us is that there is no specific pattern of the error. You can't say the higher the error, no, like the higher the rate of sale of ice cream, then the higher the error you'll be getting from the model. Yeah. So error does not depend on each other. They have different values. So they don't have a specific pattern. Let's say like the more y variable, the more the error. That's not it. What you just trying to tell is that the errors are independent. They don't follow each other. Error you have at point one is different from the error you get at point two. Error you get at point two is different from the error you get from point three. So you keep on getting different type of errors. Yeah. So from there we move on to the third assumption, which is homoscedasticity. The variance of error is constant across all level of x. There's no specific variance. You can't say because there is there is a high, you can't say because there is a high value of sunlight at this point, then we'll be having a high value of variance at this point also. If you have a high value of sunlight, as I mentioned earlier in the example, then you'll be having same variance of error. Let me say it that way. Same variance of error. Even if the sunlight is low, you'll be still be having same variance of error. If it is high, you'll be having same variance of error. All this I'm saying now might be looking somehow, but if you get to the practical points, you get it prepared. So now we move on to the next one, which is normality. Your error must be normally distributed. If the error is not normally distributed, then the data set is not fit for linear model. You can't train it on a linear model because linear model is assuming that the data set you are bringing to me must be having an error that is normally distributed. So how do you check if the errors are normally distributed? We'll discuss it next. So the next assumptions to take note of why training a linear model is no multicollinearity. That is, the independent variable are not highly correlated with each other. You can't say because for an example, let me just take another example because the ice cream and the ice cream and sunlight is not very experimental enough. So we can just say like a farmer now, a farmer trying to like grow a crop. What are the possible factors that can influence the growth of that crop? We can mention sunlight also, then we mention fertilizer, we also mention like watering. So what are the correlations between these independent variables? Are they correlated? If they are correlated, then you have to apply feature engineering. Feature engineering in terms of like trying to multiply different the independent variable to form a single variable, or dividing, or just trying to make some reasonable mathematical exploration, yeah, to just make it not having a high correlation. So if the independent variable are correlated, then it is not fit for you to like implement them on a linear model. So that was just no multicollinearity is talking about. So these 5 assumptions are the basic assumptions needed before you fit into a linear model. You have to check their linearity, their independence, their homoscedasticity, their normality, and the non-multicollinearity in terms of the independent variable being correlated with each other. So from there, we move on into how to check their assumptions. So the first one, as I mentioned earlier, is linearity. How do we check the assumptions of linearity in a model? I'm coming, sorry. So for us to check the assumptions of linearity from a data set, yes, we have our data set. How do we check if it is linear? So linearity is the foundation of linear regression. Yes, as I said earlier, it means the relationship between each predictor, that is the independent variable, like the growth of plants, and the outcome. Sorry, the relationship between each predictor, that's the sunlight, the fertilizer, and the watering. Yeah, and the outcome, which is the growth of the plant itself, is linear. So what I'm trying to talk about here is that if you try to like plot the what's it called, the dependent variable and the independent variable on the like XY scale of data set now, if you are not having a linear movement of the slope, then you can say we can just assume, you can just say that it's already nullifying the assumptions of a linear model. So we won't be training it on our linear model unless we like try to make some feature engineering to make it like form back into the linear model. So if that does not hold, then the assumption is violated. Your model's prediction and inference become unreliable. So any assumptions you make, any prediction you make, if the data set are not becoming linear with each other, then it is void. Yeah. So from there now, we'll be trying to like use some coding. Yeah. As an ML engineer, this shouldn't be like a new thing. So everybody know about this already. So what I just did here was try and why to check their linearity, as I mentioned earlier. Then how did I get if they are truly following a linear pattern? First, I imported the data set. You can see it here, x equals to df. Df is data frame. Yeah. So I've like imported the data frame up, but just for the size I have here. So I just like cut it out. So the data frame into bracket x, the value that we still implement all this ourselves. So from there, we have this image. So this is the result we got. The result we got here is trying to like tell us that the red line is the fitted line. That is the line predicted by our model. You can see that the line predicted by the model and the values itself are like around, they are following a straight district, like they are following a straight line, not that they are being scattered all around. They are on a single file, like following the same pattern. So we can say that what they are linear. So that assumption is being certified. We can move on into building our linear model. So that's the first assumption, and this I will check it. So I'll be giving out this code after this class, so you can just try to like check your model in case you want to like build a linear model also. So just try to implement it on them. So we'll move on to the next assumption, which is independence. Yes. So independence means that the residual error are not correlated with each other. Errors in point 1 is different from the error in point 2. What I mean by point one and point two is that the value you're getting for y1, oh my god, how do I explain this? Okay, so the value you're getting for the first observation is different from the value you're getting from second observation, right? So the error is the actual minus the predicted. So the error you'll be getting from each observation must not be correlated with each other. So that's what we're talking about in independence. So from there, I also implemented it using this code here. Yeah. So from this, we plot the residual over observation index to check for independence. We check if they are independent on each other or not. So this is giving us an image of like this. So from this now, we see that the error are just randomly scattered around the predicted value. You see, it is not like it is not following a regular pattern as the linear relationship. So this is telling us that yes, the model is the data set we are trying to train on our linear model is valid. It is not following a pattern. The errors are not following a pattern. This is not following any pattern. It's just scattered. So it is scattered on a plane surface here, just scattered around. So it's a very good data set to train on a linear model. So from this, we move on to the third assumption. The third assumption, which is homoscedasticity. Yeah, homoscedasticity. So what is homoscedasticity? Homoscedasticity means that the variance of the residual error. The variance is constant across all level of independence variable. The variance at the variance you get at the first value or the first value, yeah, is different from the variance you be is same as the variance you be getting as the second value. Not just because now we are trying to like predict for the farmer now how his crop will be growing. Is it that if you apply a very high amount of fertilizer, which is normal, that you'll be getting a very high rate of crop, like the crop will grow very much. So if you apply high fertilizer and then that time is the like sunny time, then you are like putting in enough water, normally we'll be expecting what? A very big crop from that farm. But this is not just telling us that the big crop we're getting from that farm is not following that. The error will be having from the predicted value. You know, our model will be predicting a value for the crop. So if the model should predict a value for the crop and then the actual value for that crop, the difference between them will always be constant. You get that? That's the variance. The difference between between the actual and the predicted will always be constant. So that's what the homoscedasticity is just telling us about. So how do we like try to check for these assumptions in the model? We also use this code. So from this, yeah. So we plot the residual versus the fitted value, as I said earlier, the residual versus the fitted value. So from there, also like we put some labeling and fit in the linear regression model, and we got this. So from this also, we are seeing that it is not that they are following a same pattern. They are not following. We are not saying that because the residual, because the fitted value here is higher, then the variance there should also be higher. No, the variance are constant all across. You can't say because it is bigger here, then the variance will also be bigger. It is smaller here, the variance will also be smaller. The variance are like normally distributed, not even normally, this is not normally distributed, are just evenly distributed. Yeah, that way. The variance are evenly distributed for an homoscedasticity assumption. So if our model, if our data set could like fit in for this assumption, then it is making a very nice. So we move on to the next assumption, which is normality. Okay, so why the regression line can still be estimated without normality, blah 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 blah. What this is just telling us is that normality, in the sense of statistics, is that the values are much concentrated at the mean. Just yeah, just that way. That's the simplest way, although it is not very nice enough. So normality is especially critical in small samples, because if you're having a small sample, it is not representing the population properly. So having a small sample is very, if you have a small sample for a data set and you want to employ it into a linear model, then you have to check for the normality. You have to like pay extra attention on the normality of the data set. But if the data set is very big, there's something called the central limit theorem in statistics. The central limit theorem is just telling you that if you have enough big data, If you have enough big data, then it is fit for representing the population itself. That's not the way it was stated, but just like for normal understanding. So if you're having a very big data, then it is fit to represent the population. But for a very small sample, then you have to like pay extra attention in checking for the normality of the data set. Yeah. So from there, we also computed it using this equation again. Oh, sorry, I said equation. Using the code, yeah. So first we fit in the linear regression model, then we predict and calculate residuals, then we plot residual versus the fitted value, blah 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 blah. So after that, we got this. Oh no. I was just rushing. So there's a small error. This is not what I was intended to put here. So I've just maybe when compiling this slide, because the time was also too short, I just out of this stuff yesterday. So we'll just move on to the next. But I think you just try to understand what I was talking about, the normality. If you can just check for the normality of the data set, then you can move on to the next assumption, which is no multicollinearity. Although I'll still come back to the normality. So we know how to like go about it, how to test it also. So we go to the next one, which is no multicollinearity. No multicollinearity, as I said earlier, is when you are having maybe like two or more independent variables. If you're having two or more independent variables, as the farmer now, having the sunlight and then the fertilizer, check if the fertilizer and the sunlight are they correlated. If they are correlated, like highly correlated, then that is not a valid data set to fit into a linear model. So if they are highly correlated, they're already evaluating their assumption. So you have to like perform some feature engineering, or you just remove some independent variable to just make it fit into the assumption of a linear model. So the next one, we also have its code here. But we won't be going into this because this is having much. I've made some codings ahead before this, which is like having the X1 and X2 and X3. The X1 here can be like, let's just say, representing the fertilizer, X2 here representing the sun, and X3 representing the water. So these are the VIF I got from them. So from there also, we got this. So what I did there was like setting a threshold that if the Y value is greater than 10, then they are having a very high correlation between each other. So I will be taking them, or I just try to like find a way of manipulating them to like have different correlation from each other, or I just combine both of them to check if they will still be having that same high correlation. So that's what I did there. Then I think that's the end of the assumptions. So from there also, now moving to like just making a summary of all what I've been saying, the assumptions of the model. So the first one I mentioned, the linearity. Method of checking linearity. Just method of checking the linearity. But I just like stayed on three. So which are the scatter plots, the residual plots, zero tests. So these three methods are best fit for checking the linearity of a model. And we have the scatter and residual plot. So we've checked them before. The next one is the independence. What are the methods checking for the independence? That's three points of checking for the assumptions of independence in the data set. Yes. So the W-Watson test, the residual versus time order plots, yeah. Then the autocorrelation function. Although in this slide, I just mentioned the residual versus time order plots because this W-Watson and autocorrelation function, they are very deep. So I don't want to like jinx us with a lot of statistical calculation. So we just move on to the next assumption, which is homoscedasticity. Homoscedasticity also have three basic method of checking their assumptions, which is the residual versus value plots, the scale location plots. Yeah. So those are the basic three method I can like vouch for you to use in testing the homoscedasticity of a data set. So the next one, which is normality. Yeah. So the error I made at that point there. So if you want to like maybe make some other investigation on it, like try to like make your own personal research, then you can like try to use the histogram of residuals, plot them against their frequency, plot the data set against its frequency, check if they are having the highest frequency at like the middle points, just try to check it out. So this Shapiro weak tests, those are deep statistical tests. Then the QQ plots, that quanti plot. So why I didn't use this is because okay, no, let me just so let's just move on. The last one, which is no multicollinearity. This no multicollinearity is just, you can just do it from basic correlation. Just apply basic correlation to the data set. This can be done on SPSS, Excel, or any statistical app. So that's that for that. Then I also brought out three model for it. Like three method of checking if the data set is having the multicollinearity, is fulfilling the multicollinearity assumption. Yeah. So for the variance inflation factor, which is what we presented in the slide, then the correlation matrix, as I mentioned now, which is the Pearson. The Pearson, yes, it can also be like the rank based on the data set we are having. So if you're having a data set that is being ranked, then you don't have to use the Pearson here. You have to use ranked, like the correlation matrix, rank correlation matrix. Yeah. So for that, the third one is the condition number. Yeah, that's still okay. So I think I can just have this stop for now. So if you have any question before we move on to the next section, please signify. Hello? Any question?
Okay. Does anyone have any questions? Someone's hand was raised before while you were speaking. I don't know if
Oh,
the person. Yeah,
oh,
but
sorry,
it's
I
like the
didn't.
person. Oh, that's
Yeah, Paul.
okay. And that person. So,
Yeah.
All right. So, good evening, everyone. Um,
Yeah,
so,
good evening.
I've you said severally correlation, 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 correlation. So, I'm just trying to understand: does it mean direct link? Is it like causation? Is it causation like A is directly affected by B, or what does correlation mean exactly? I know this might be a very weird question, but I'd just like to understand that. Thank you.
Okay, so correlation basically in statistics is just trying to like measure the relationship between two variables. Are they positively correlated in the sense of that moving in same direction, that the higher one goes, the other also follow, or the lower one goes, the other also follow. So if you're having there are different type of correlation. We have the positive, negative, perfect positive, then perfect negative. So based on what you want, like try to calculate on. But what I'm just trying to talk about under the no multicollinearity model assumption, yeah, no multicollinearity assumption is that for your independent variable, you have to like check if the independent variable are having a high correlated value with each other. You grab if the independent variable are having a high correlation of more than 0.5, then it is already voiding the assumptions of a linear model. You can't train that data set on a linear model. But if you're having a very low correlation between the independent variables, then it still fits, like lesser than 0.5 is still okay. If you're having a correlation lesser than 0.5, the lesser it is to 0.5 to 0 is a very good assumption. Like this is like verifying the assumption of a linear model. So that's just what I'm trying to talk about. If the correlation is too high, please don't use it on a linear model because you're avoiding the assumptions of a linear model. So any other question? Or does that answer your question? Paul?
Yeah, it does. Thank you very much.
You're welcome. So any other question, please, before I proceed to the next one? Hello? Okay. I think there's no other question. So we'll move on to the next one. So the next phase, which is when to trust your linear regression model. Yes, we've satisfied our regression model from its assumption. We've satisfied all its assumption. Now, how do we trust if the linear regression model is giving us the exact value? Why is it not biased? Is it accurately? Yes. So let's check. When should we trust the linear regression model? If the assumptions are satisfied, yes. If the assumptions are satisfied. Then the next one, high predictive performance. Before trying to like work on any data set, what I usually do is, even before I just even import it on Google Colab, I usually split my data sets, because having a splitted data set is just like trying to like give it a real life data set that it hasn't experienced before. So I usually even split before even importing on Google Colab. I don't know why, but I feel safe doing it that way. So you have to like check for high predictive performance by trying to like test the model on your splitted data set before training the model. It is not even for you to like, there are some stuff we're supposed to talk about at this point before trying to make your tests, before trying to test the sample. Yeah, before trying to make the prediction on a test sample, you have to like split it even before making the what's this thing called? Um oh my god, I'm coming. Uh, feature scaling. Yeah. So you have to like split up the model even before feature scaling, because in statistics, normally for feature scaling, we already understand how it works. So what it is doing is that it is trying to like find the mean of all the data sets, then trying to like implement it to scale that data set on it. So if you are like trying to say, okay, now let me just apply feature scaling, then after the feature scaling, I split my data set. From you applying the feature scaling with the test set, it's already been affected. The data set is already been biased, because for you to like compute it, feature scaling, you need the total mean of the data sets. And for you to get the total mean of the data set, you're already implying it on the training set and the test set before splitting it. So that's already causing biasness on the data set. So high predictive performance. Let me go back. So the high predictive performance is like, yes, on the test set now, I'm trying to like test the model I've built after satisfying the assumptions on the test sets. If I'm having a very high predictive performance, like an R score of like, let's say like 0.7, 0.8, 0.7, 0.9, yeah, that's very great. Or one, that's it can be great, but it will look overfitted. You'll be scared of yourself. Yeah, this is being overfitted already. Because how can I have another score of one? It has to be like checked again. You have to check up the model again. So AI predictive performance is okay, but not up to one. 0.6 down to 0.9 is a perfect predictive performance. So we move on to the next one, which is data is within the range. For regression model, people usually make this error of like trying to extrapolate in the sense of like, now I train my model within the data range of 1 to 5. It is just, its calculation is based on that range. If you are trying to like predict a value outside that range of 1 to 5, then you're already extrapolating. And regression does not support extrapolation. It is very good extrapolation, like data within the range. If you like predict 2.5, which is between 1 to 5, or 3, which is between 1 to 5, then regression model is the best fit. But trying to predict 6, that accuracy, it might give you a very nice accuracy, but the trust you have on that model shouldn't be as when it is between the range. So that's what I'm trying to talk about there. So now, the few influential points or outliers. It is normal for you to have outliers in data sets, but we have to clean it also, yeah. But there are some outliers that they are not just point alone. They have contribution to the data set, just like you trying to measure the height of students in a school now. Then you go to a government school. In government school classes, you see some people, their heights are not compared to some others, because some are like after maybe several years they are coming back to school to learn. So you can't just say that because their height are like in outrange of others, then you are removing it from the data set. They also contributing to the height of the class. So they are influential points, but it shouldn't be too much. So that's what I'm trying to talk about here. It shouldn't be too much. If you're having too much outliers in the data sets, then you shouldn't trust that model, because it might be like be biased of following, or be biased of being influenced by those outliers. So a few outlier in the data set is still okay. We can't say because they're outlier, then we delete them from the data set. They can also be the main reason why we're even working. So everything has the advantage. But a few is still okay. So we move on to the domain logic aligned with the model. Yeah, exactly. Because now we're talking about the farmer now, trying to measure his crop like growth based on some independent variables. Now, the farmer has been measuring his yam, or let me say yam. Is has been measuring his yam at the rate of like maybe 5 centimeter, for an example now, not 5 centimeter, that's 5 centimeter, 10 centimeter, 12 centimeter. Then suddenly your model predicted a value of like 200 centimeter outcome. That domain logic is out of bound. You can't like take that into that model has to be suspected. It has to be like examined. It has to be diagnosed. So that's just what I mean about the domain logic. Does it align with the model? I'm training a data set of 2 centimeter, 5 centimeter with my model. Then it is giving me an output of 200 centimeter. That's out of range. So that's just what I mean about the domain logic. So the first one now, we're starting the practical example, getting a data set. Getting a data set is one of is the backbone of machine learning. If you get a data set that is bad, no matter how perfect you are in building a model, the model will be bad. If your data set is being polluted, even if you use deep learning, you use everything, you combine them, you ensemble them, you use pre-trained model, it will still be bad because data set is the definition of the model itself. It is what defines the model. So now there are several ways of getting data sets. You can check some open source such as Kaggle, data sets, ORI, and a lot of them. So just online, you can also go to public what do they call themselves? Public sources, yeah. There are also public sources that like store data sets for academic purpose and like experimental purpose. So those are how we get data sets. And there are also some I don't want to talk about that. So the ETL, the ELT, ways of getting data sets, streaming data sets, APIs, and those are also ways of getting a data set. So from there, we won't be going much. As I said earlier, I already found us a data set we'll be using to implement on these assumptions. How do we check the assumption to verify how the assumption works? So we'll be using the data set I've fine-tuned, I've cleaned the data set. So I'm assuming all of us at this point now, we know how to clean data set properly. Yeah, so next one is moving to the preprocessing the data set. As I said earlier, the cleaning of the data set. We all know how to clean data sets. We are machine learning engineers. I'm just making an assumption. If I'm wrong, please come to my attention so I can just like glance through it for you. So from there, we move on to the next one, which is like checking for the assumptions. Yes, we've gotten our data sets. Yes, second step, it is being cleaned. Then the third one is checking for the assumptions. Most ML engineers don't do that. After preprocessing the data sets, because the stress they've passed through from getting the data sets, cleaning the data sets, what they just want next is to train it on the model and then start predicting. But you have to check for the assumptions also, because if you don't check for the assumptions, you don't know what the model is expecting. So if you are giving in a very bad data set to the model or what it can't understand, it will just give you what you also can understand. So that they'll move to the next one, which is training the model. So after checking the assumptions properly and satisfying all the assumptions of the model you're trying to predict on, the linear model you're trying to predict on, if we have time, maybe probably we have some chance by ML Lagos, maybe they can have some time with us. So I can just go through the non-linear models as well. But for now, let's just focus on the linear model we're talking about. So you check on for the assumption of the linear model, you train the data sets on the linear model. Then you also go by to making your predictions. Yes, you make your predictions. So there are some, yeah, everybody can make this. Yeah. So we'll move on to the next one, which is interpreting the results. So I provided some link here. The link at the first one, which is getting the data sets. This link is where I store the data sets. It's on my drive, so you can view it from there. So we'll be working through it together. We'll be making some experiment now. So we get the sets, download it, then we check for assumptions, which is for this is the link for it here. So I've written all the code. So we'll just move through it step by step. And if you have any question, I'm open to it. So we move on to getting the data set. So I'll just copy this code right now. Sure. What's that? coming, sorry. So I was trying to copy this code earlier. So we copy the code, then we paste it on our browser here. Okay, still loading. So here we go. Yeah. So the data set is very, very minimal. So we can just like try to see what is happening in the model. You know, if we like try to bring out a very big amount of data set of thousands of rows, thousands of observation, we won't be able to like grasp what is going on. So I just picked 31, like just 30, yeah, let me say just 30 observation for us to just like experiment on. So we download this data sets. So it will be downloading now. Then we move back to the second link, which is to have pre-processed the data. As I said earlier, these data sets have been pre-processed. So now we move to the checking of assumptions. So we copy this code also, then we'll paste it to check for our assumptions. Since we've gotten the data set, it has been pre-processed, then we are checking for the assumptions using this code. So I'll be sending this file after now, so you can also check for your model before training them on a linear model. Yeah. So we paste it here also. Then boom. Sorry, before I move on, I hope all of us are good with using Google Collaboratory. Hello. All right, all
Yeah,
right.
I am.
So we move on. Okay. So this is still opening. I'm coming. Loading, 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 loading. All right. So here we go. So the data set is named salary data. So I just downloaded this as shown earlier. So we have to like import it into the notebook using this.
Oh, you're
So uploading
not
it.
showing.
Sorry, they say.
Your notebook is
Hello.
not showing. It's still showing slides.
Is it showing this slide? Okay. Oh my God, I'm coming. How about now? Are you seeing the notebook now?
Yes.
All right. So there's this stuff about Google Colab. For you to like connect it to the Python 3, you have to just first run this. Normally to give us an error because I've not imported the salary data. But for us to just push it, give us an error. We have not imported the salary data. So for now, what's so what to work on this the salary data? The salary data is consisting of employees' years of that, like their work experience, their years of work experience, then their salary. So we are trying to predict their salary based on their work experience. I know this will give us an. So from here now we'll try to import the salary data. We click on this, then it will be on our download. That is it. So open. So since I've imported the salary data now, then we run this cell. That's for importing the data sets. Yeah, you can see it from here now. These are the years of experience of each individuals, and these are their salary. So for this first person now, the person has worked for 1 year, 1 month, and the person is receiving the amount of $39 343 because this can be naira after working for 1 year. So that's just basically what we're working on, trying to like predict the salary of each individuals based on their years of experience. So there are different years of experience and different type of salary here. So we're trying to like build them on a linear regression model. So the first thing we have to do is to check for our assumption. And the first assumption mentioned earlier is the linearity check. We have to check if the years of experience and the salary, are they both linear? Are they following a linear distribution? No, sorry. Are they linear? Yeah. So are they following same pattern? So we go this way. The code I wrote earlier on the slide. So this is how it's been implemented. So you can just try to like manipulate these years of experience. This years of experience is like trying to like point out where the X data are. So if you're having more of this X data, then you can add like a comma here to like include other data sets, but it won't be like fit for plotting on a two-dimensional scale. It will be giving, you have to like plot it on a three-dimensional stuff like that. So it will be very complicated to interpret. But for simplicity and easy computation, we'll be just using a two-dimensional plot. Yeah, a two-dimensional plot. So boom, we have this. So this is just telling us that this is the fitted line of the regression model, and these are the like the actual value. You can see that they are following same pattern. They are not like just being scattered around. There's no 1 year, 1 year, 1 year. They are following same pattern. The higher this goes, then the higher the X goes, the higher the Y also follows. So the higher your years of experience, the higher the salary you get based on so if you work, the more the years you work, the more the salary you get. So that was what this image is trying to tell us, that it has satisfied the linearity assumptions of a linear model. So this is satisfied. Then we'll move on to the second assumption, which is the independence check. How do we check if the um, residuals are not dependent of each other? For the residuals to be independent of each other, then they have to be scattered. Like they don't have to be like follow any pattern. So we'll be running this data set now. My God, it's time for solar. I'm so sorry for rushing this. So we just have to rush it now because I'll be going for solar now. I'm so sorry. So this is what we have now. After running that model, we got this. So the data set is telling us that the errors are not following a single pattern, an identifiable pattern. Or can you identify any pattern from here? No, we can't identify any pattern. They are all scattered around the predicted value. So just randomly scattered. So you can't just say because this one is following this pattern now, the next prediction is to follow this pattern. That's wrong. If you can get a pattern from a regression model, like from the data set, then you don't have to use that data set because it is nullifying the independence assumption of a linear model. And the linear model assumption is that the errors have to be independent of each other. So that's just what this is telling us now. So move back now to the homoscedasticity check. Now, why we won't be running this homoscedasticity is because we have just one. I'm coming, sorry. Yeah, that's multicollinearity. Yeah. So for the homoscedasticity check, yeah, we'll be running this. Yeah, sorry, I'm so sorry. So for the homoscedasticity check, we'll be running this to check for the residual versus defeated. How does the errors, how are they different from each other? Are they having same variance? Hope it is not that when a certain value goes up, then the variance of the error also follows it. The variance of the error has to be like constant. It doesn't change. You can't say because a higher value here is giving us a higher value of error also. A lower value here is giving us a lower value of error. No, the variance of the error has to be like equal throughout the data set. So we also run this now. I'm so sorry for showing you guys, but so for this now, this is what we got. This is like trying to like tell us that now the errors now are having constant variance being spread all around. Not that when this is increasing, then the errors are also increasing. The errors are being spread all around. You can't just find a single pattern. There are constant error being varied all around the predicted value here. So now we move on to the multicollinearity. Multicollinearity, as I mentioned earlier, is just for trying to like find if two dependent variable, two or more independent variable are being correlated with each other. But for our data sets, we are just implementing a single independent variable on the salary, which is the years of experience. So we can't implement the multicollinearity here because we just have one single value. So we'll skip this part. Yes, we'll skip the part because it will just be automatically skipped. Yeah, because we're not assuming a single value for the independence variable. So that's what we got for that. That's all for the assumptions. So after the assumptions, now going back to the slide. Are you guys seeing the slide? Oh my God.
No, it's still your notebook.
Okay, still my notebook. All right. So let me change that. I'm coming. I'm coming on. Oh, pressure's on me already. Okay, let me just go and copy the code. So just I don't what I just try and go back now. Okay, I'm coming, Mr. Frank. I'm coming. So what you just do here now is I'm just going back to the slide to copy the code for training the model. So I'm not doing much from the slide. I'm just trying to copy the code. Then I'm coming back to this, then pasting it here. So this is the link for like training the model itself. Since we've like ascertained that the assumptions have been satisfied, so we are trying to like train the model right now. So we move on to the first one, which is like importing the libraries. Then we import the libraries. Then importing back the salary data itself, because now we are training it as an ML engineer. Because for that assumptions we did earlier, that's the basic rule. You have to just like try to find the assumptions. Most ML engineers just fly straight into the predictions, but now you have to like check for the assumptions for proper training of the model. So now let's import the salary data. So we're importing the salary data this way. What's this? So this is the salary data now. Then we have to like start running from the importing data sets. So what this is trying to tell us is x equals dataset.ilog. That is, it is selecting just the first variable. It is selecting all variable except from the last one. And the y dataset is selecting the dataset except from, it is selecting just the last dataset. It is not picking from every other dataset. That's what this -1 is just trying to tell us about. So from there, we'll move on to the splitting. Yeah. So you split your dataset before doing any stuff. If you want to like make some feature scaling or any stuff, try to split your data first. That's the best. That's the first assumption you have to like make. Split your data first before any calculation, before any manipulation. So next thing, we have to train the model based on our x and y data set that have been splitted. So that's what we are doing right now. We are training it, so it has been trained. You can also like I pattern this, but we won't be going into that. So let's just move on. Let's just move on. So we move on to like predicting the test results. You know, we fitted the test result and we all let me engineer. Why am I saying this? So we move on to the Y prediction. Yeah. So we predict for the X test. So after predicting it, then we visualize the training sets. We're trying to visualize the training sets. How is the training set? How did the model like try to predict? How is the model working on a prediction? So we got this also still running. Okay. Boom, 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 boom. So we see that this model is like, if not perfectly accurate, a model can't be perfectly accurate, but at least it's still trying to like print out some sense. Not just that the arrows will be there, the predicted values will be here, then these values will be scattered all around. I hope you're getting what I'm trying to talk about. So the predicted value is closer to the actual values. The actual values are represented in this red boxes here, and the predicted value is the blue line here. So we can see that the blue line, which is the predicted value, is close, if not even passing through most of the actual values. So it is close to the actual values, yeah, but not accurately, but it is still better than just random guessing. That's what we're doing probably. That's what we're doing machine learning. So we also have to like check it on the test sets. Now that we've visualized it on the training set, we also want to check it on the test sets. So we also run this code here. I'm supposed to explain all this code step by step. We're supposed to build them together, but just because of time, so we just have to move on. So this also for the test sets. You know, the test sets is having a very minimal amount of observation, because I set it here to be 1/4. That's quarter of the whole data set is what we'll be using as our X test. So you can also like try to like play around this. For the 1/4, we are just having three data set of 1, 2, 3, 4, 5, 6, 7, 8 of 8 data sets. You can also change it here to be around maybe 1/3. That's like 30 points, 33 points, blah blah blah. So we've changed the test size now. So the test size will be more. So we have to like train this now again because the X chain would have changed. Then the Y predicted would also be changed. So this now. So I'm just trying to like show how the test set is working on our predicted value after following the assumptions of the linear model. If you follow all the assumptions of the linear model, then you don't have to start fighting yourself with trying to like hypertune, or although hypertuning is very okay, just like this model that we have here now. If you have to like make it on a real life problem now, we have to like hypertune this model because it is not working perfectly. Just hypertune it a little just to like make it fit in properly, So that's also what we'll be talking about just based on time. So the 7 data sets we have before, 1, 2, 3, 4, 5, 6, 7, 8 is now 8 now. Can you see this? So it has increased a little bit. So that's what we are just talking about for the test set. And we can see that the predicted value is also working almost perfectly for the test set. It is even like out of 1, 2, 3, 4, 5, 6, 7, 8, out of 8 samples, then it is like accurately predicting 1, 2, 3, 4, 4 out of 8. And this remaining one, this 1, 2, 3, 4, this one is even closer. This is also closer, but unlike this. So this can just maybe from our hypertuning, maybe we can just capture more of it. But I think this is the best the model can capture for now, based on our training. So from that also, if you want to like try to predict for a single value, like for a single person, maybe someone just comes to your office, now based you have this data set already, you've trained your model, you now want to like predict for the person coming into your office, what should this person's salary be based on his working experience, based on his years of experience. Yes. So we can just use this other code. So this 1.1 is just centralizing on 1 year, 1 month. So if I should come to your office and I'm telling you that I've just worked for 2 months, that should be 0.2, right? 0.2. This 0.2 I'm putting in here now. According to what I said earlier, regression does not fit in properly for extrapolation. So the data set I trained it on, let me try to view the data set here. So the data set that was being trained on was just at the range of what 1.1, which is the smallest from here, to what 10.5, and I'm not trying to predict 0.2. That's extrapolation. It is outside the range of the years of experience. The value I'll be getting should not be trusted. So that's what I'm just trying to talk about. So if you want to like predict for someone now, check if the years of experience the person is bringing to you is within the range of the years of experience used in training the model. So if the years of experience is outside this range, then you shouldn't trust the result of that prediction. Although you can still use it, but it shouldn't be trusted. You can just assign like maybe 60% of assurance because it is a model. It shouldn't be 50, which is better than random guessing. So if that should be the case, 0.2 now should be very low. That's it is only because the result. That's $28 685 because it can't be naira. So I just assigned dollar there. Okay, so that's it. Now let's just find a value within this range. 2.9, 2.2. Let us pick 2.4. So 2.4, which is within the range of 39,891. 2.4. Let's go check that. 2.4, 2.4, 2.4, 2.4. So predicting this now, we're having $49,246.45. So this is the price for a person who are like for an employee who have worked for 2 years, 4 months. So let's go and check it to the data set we have. That's 49 to 46, 49 to 46. So from this data now, 2.4 should be around there. 2.4 should be around there. And this 39 to 56. So our 49 is within this range. You see, the model is working, if not perfectly, but still okay. So this change here can be approximated, maybe based on some other evaluation by the maybe the CEO or the employee, maybe just trying to evaluate this to a very nice figure, maybe 49,500 or 49,300. So based on how the employee has been evaluating the worker. So from there, I think that's the end of the lecture. So if you have any question, please, you have me now. Hello.
Yeah, sorry.
Oh
The
yeah,
domain, the
the fan.
domain logic, the domain logic you talked about, is it similar to interpolation, extrapolation rather? Yeah.
Yeah, exactly. Interpolation, extrapolation, like what I just explained now. If the domain knowledge, in the sense of like this thing that we just did now, the 2.2 now, if we should like try to make a prediction on it, it is outside the range of the value. So it is most likely that the value we'll be getting is not being trained from the data set. The model does not understand the values that are outside of the range it was being trained on. Just like a child. If you train a child based on some fruits, then you take the child to the jungle trying to identify a tiger. It will be like it won't understand. You grab. So based on the value it was being trained on, it is fit for us to like ask about that range, not outside the range, not below the range. You grab what I'm trying to talk about. So that was, I mean, did I answer your question very well? Hello, Mr.
Yeah,
Frank.
yeah, yeah, yeah. Yeah, you
All
did.
right, all right.
Thanks.
So
So
any other
one,
question?
one question, please. The uh, the part of checking for linearity, how do you do that with multiple variables? Because it would be hard to visualize. This one now is a
Exactly,
2D.
exactly.
So do you check for the variables one by one to see maybe each independent variable against dependent variable, or maybe there's some kind of sklearn library that can compress it
Okay.
to 2D. I don't know.
Yeah, that's true. That's true. You can apply some dimensional reduction analysis on it, or some feature engineering. If you have that, my best advice is, because if you should try to plot it on a 3D, you need a very technical knowledge to interpret the results you'll be getting. So what I would advise is that transform the independent variable first into a dimensional regression, then find the linearity between the variable, the dependent and the independent variable. Then from there, the dimension reduction analysis to give you like a variance explanation of your data sets. So if you like have a variance explanation greater than like 0.7, 0.8, that is the new value from dimension reduction is having a like an explanation of 0.7 or 0.8 from the dimension it was being brought down to, then it is very advisable scale to check for the linearity. You grab board. Trying to like implement them on a 3D scale, 4D scale, 5D scale, it's very complex. So the best advice, use dimensional reduction analysis. Then check for the explained variance. If the explained variance is very high enough, then you can plot it on to check for the linearity. Is that okay, Mr. Frank?
Yeah, okay, but it is. I've realized that many of these dimension reduction techniques, they work without the labels. That's like unsupervised, just by themselves. But this one, but we're trying to see if there's a linear relationship between the independent and the dependent, the labels. So, is it possible for us to take each of the variables, the independent variables one by one, and then match it with the dependent variable, like in a 2D plot? I don't know if that will maybe because I'm looking at a situation where if you
Okay.
have like six variables and then maybe five are linearly correlated, but the sixth one is not. I don't know if that would be a good idea to a good
Okay, I
like
know, I
situation
know, I
for us
know,
to
I grab what you're talking
drop.
about. So, hello, can I proceed?
Yeah, yeah, yeah,
All
yeah.
right. So, for that case now, my best advice for you is to perform the multicollinearity test first. If you should perform the multicollinearity test, it will identify the independent variables that are having high correlation within each other. So you can terminate them or apply feature engineering before trying to like find their linearity. Do you get that?
Oh, okay. Yeah, yeah, sure. Yeah.
Yeah. So you apply the no multicollinearity first. Try to check between the independent variables. Check their correlation first. If they're having the ones with the higher correlation, then you try to like maybe minimize it or dimensionalize reduction analysis, or you just like delete them or feature engineering. Just try to find a reasonable mathematical like expression to like justify that solution there to make sure that the multicollinearity is not being void at that point before you now try to find the linearity. So it is possible for you to like find one assumption before the other. It's not that it has to follow the systematic way I've given it. You can find the no multicollinearity first before going to the linearity. So just randomly, but you have to like make sure that your data set is following like is accurate on those assumptions before training them on the linear model. So that was what I'm talking about. Any other question? Oh, Mr. Frank, is that
Yeah,
okay?
yeah, yeah. That's okay. Thank you. So
All right.
that normality part is I didn't really get. Is it that the normal? Is that the errors should be normally distributed? I didn't get that part. I know I
Yeah.
understand the homoscedasticity part. The variance should
Okay.
be yeah, but the
Constant.
normality is it that the errors should form like normal distribution stuff.
All right. All right. I
I
got that. So, oh, okay. Any other thing?
no,
Okay.
no,
Let me
that
continue.
that's
Then. All right. So what the normality I'm trying to talk about is this now. For a real life data set, normally normality is just being theoretical. It has never been normal. No data set is normal. So if what I'm trying to talk about normality is that the errors you are getting, not the data sets, the errors you are getting from the actual minus the predicted value. The actual value you have it with you, then the predicted value from the model you also have it with you. Then if you like make a subtraction between the actual and the predicted, the errors you'll be getting from it, plot it against a frequency table or a time series. Then if it is following a normal distribution, then it has satisfied the normality assumption. But if it does not, then maybe you just try to like use some transformation techniques such as log transformation, maybe what else? All those transformation you have, just try to transform the data sets before finding the normality. But it has to like make sure that it follows the assumption. It's past the assumptions of normality. If it does not pass the assumption of normality, then the data set is not properly okay enough. Hello?
oh, okay. Yeah, I get.
Yeah.
So I don't know. So can we say that that variance and that normality assumption are kind of connected?
No, they are not connected.
Okay. Okay.
Variance is different from frequency distribution. Plotting variance against error, yes, is different from plotting the frequency of error against the error itself. We're supposed to like make some real calculation of statistics, but based on the limited resources. So we just like move on now. What I'm not trying to talk about is that normality is different from checking for equal constant variance. Let me find a formula for you. Okay, if a data set is having an error that follows a normal distribution, then the expectation of the error will be zero. Do you get that? We have to solve these things step by step. Are you a statistician? I'm sorry.
Yeah, I have some. I've taken some courses on data science
All
already,
right.
so that's the
Okay.
thing.
So for a normal distribution, it has two parameters, which is the mean and the variance. You get. So the mean of an error for a normality distribution will be zero. Then the variance will also be what sigma squared. So if you're having an error, you know, having mean is different from having variance. So the variance being constant is different from the error following a normal distribution. So you have to like check for both of them separately. Check if the variance are having a constant, are being constant. Yeah, are being constant. Then the errors are being normally distributed.
Okay, okay. So I think the idea right now is the variance applies to the data set even before prediction. Like for instance, you're trying to compare uh, um, the amount spent by people on food. Somebody can spend 500 naira, someone can spend 10,000. That's like, okay. So you might have to apply log on that so you can make the numbers smaller so you can plot it. But the error is
Yeah,
when you are predicting from that x variable. So the error so basically the error just applies to your predictions,
exactly.
how far
Yeah,
your predictions are from the expected value, while your
actual
variance
value.
applies to the data set gone gone, like the
Exactly. Yeah, yeah.
okay, okay.
You grab that.
So
That's correct. Yeah. I missed
okay,
a lot.
but the solution for it now, if the for the variance, if the values are too far apart, like this example of um um let's say one of the variables is like how much people spend on their food, and it's too large. Like you have somebody spending um 500 naira, someone spending 10,000 a day on food. That's too large. So if you have that kind of variance, you can easily apply log transformation, right, to to make them within. But for the case of error not being normally distributed or not being close to normal distribution, is there like a way you can solve that?
Okay. You said if the errors are not like following a normal distribution, right?
Yeah.
Okay. So my best advice on that is that you discard the data sets. Although
Okay.
I'm sure there will be a solution to it. I'm sure there will be a solution. But
Okay.
or with if we can like transform the position of those observed data sets, like the data set one taking it to like data set five, data set two taking into like data set four, just like trying to like randomly reselect the observation from their position. Because it was having a fixed position initially. It was the reason why we're having that error not following the number distribution. So if you like can try to like manipulate the position of those observation, like the position of observation one going to like observation five, observation two going to observation three, just like randomly selecting them, then there's a very high possibility that you'll be having a normal distribution from the errors.
Oh, okay. All right. Oh, okay. Okay.
Okay.
Okay. Yeah, that makes sense. Yeah. Okay.
Yeah. So although there will be other statistical method that we can use for that, but I've not like been into it properly because I've
Well,
not
I think
experienced it.
it can also be as a result of outliers, right? So maybe if you can remove the outliers, I don't know if that
Mm,
can
at times,
affect the error.
outliers. Oh, we might need to round up
If
soon.
that's
Yeah.
too much.
All right. So
If,
what is this now, Mr. Frank? Hello.
yeah, 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 yeah.
All right. So what is this now? Outliers or not outliers? If you are the one that generated the data set yourself, then you can vouch for something to be an outlier. But most time, people like remove the real information of the data set, like trying to assume that they are outliers. It is wrong. There are some, although you cannot like try to find the normal distribution, then find the variance, then to remove the outliers. There are times that even they are the real information for a data set. They might just be like out of range, but logically they are part of data. So removing them from the data set is already making the data set biased. You grab. So I cannot say that
Yeah.
removing the outlier, although it is good to remove the outlier, you have to have like few outliers, as I mentioned earlier. Having few outliers is reasonable for a linear model, but having them too much is bad. Normally, you have to clean your data set, remove the outlier, but removing all the outliers is already spoiling the data set already. You're having half-baked data sets. It is not well estimating the population. Yeah, that way.
Oh, okay. Yeah.
Yeah.
That makes sense. Thanks. Yeah.
All right. So, any other question, please? I think we'll be running off soon. How do I miss my salad? All right. Any other question? I think someone was raising his hand at the time. What was that?
Yeah, it was Frank.
Uh, all right. Okay. Okay. It was Frank. All right. All right. So, can
Okay,
we call
me.
it a day? Okay,
Yeah,
I'm with you. I'm with you.
well, yeah, yeah. So, I mean, if Frank still has like more questions, he can reach out to you so that we don't
All
just,
right.
stay on the phone for 2 hours each. Yeah. So, yes, thank
Yeah,
you
that,
very much,
you're
Assisi,
welcome. You're welcome.
for presentation and for your session. It was quite interesting, and honestly, I was like, okay, this is something that I've not thought of before. But I
Wow.
mean, yeah, yeah, it makes a lot of
Yeah.
sense. So yeah, just to wrap up, we're already rounding up, like in the next 1 or 2 minutes to be done. So yes, follow us for more updates, to know when our next session will be, and this time we'll let you know. We will be opening, I think at this point we'll be opening our technical sessions to more community members that have technical talks like this, so that we'll be able to know who and who is in our community. Follow us for more updates, and you know to know what we are doing. Then upcoming events, we'll be having our August office hours, and we'll be having our August technical session. And yes, to everyone who filled the form for volunteering, you'll get an email either this night or tomorrow morning. We got a lot of um responses, and we're going through them one by one. So yeah, be rest assured that you get a reply if you applied. So I think that brings us to an end. Yeah, we like your feedback. Please give us feedback. That's what keeps us going. We love your feedback so far. It's something that is pushing us, and we are grateful for how we've been handling all the sessions and all the activities in the community. Thank you very much, everyone, and have a lovely evening. And yeah, happy new month in advance. The month,
Yeah, same to you.
yeah. So, bye, everyone.
Yeah, bye.